Bismillahirrahmanirrahim. Assalamu alaikum. Hello, everybody. I'm going to present a tutorial on the generation of two-level and three-level switching signals for power electronics converters using space vector pulse width modulation. The content of this tutorial, we will give a short representation for the space vector concept of sinusoidal three-phase voltages. Then we will move to simplifying two-level inverter topology and identifying conduction states of this inverter. Then we will give also a brief description of the pulse width modulation concept. Then we move to the detailing of the two-level algorithm. Then the simplification of the three-level inverter topology and identification of conduction states of this inverter topology as well. Then we go to the detailing of the three-level algorithm. The objective of this tutorial is that by the end of this tutorial, each one of us can be able to either make the algorithm from scratch or understand at least the already existing model which I present on MATLAB Exchange server. The space vector representation of a three-phase quantity, as this two graphs depict, is simply one compact representation of three-phase quantities. If we see this black vector, it is an instantaneous sum of three vectors, three individual vectors, which are changing their magnitude, but their angle is fixed in space. So the resulting vector is always rotating in this fashion. And in this way, we can either represent the three-phase quantities with this sinusoidal representation or with this three components, three space vector components, or with only one resultant space vector like this black one. Therefore, the space vector is the vector sum of the three vectors representing the three-phase quantities VA, VB, and VC. Also, three-phase quantities VA, VB, and VC can be expressed in the form of an equivalent set of two perpendicular vectors, conventionally named alpha vector and beta vector, V alpha and V beta. It turns true that a three-phase set can be equally represented by any of these four equivalent representations. The two-level inverter topology, as we used to see it, is composed of 6 switches. Each switch is composed of a transistor, power transistor, IGBT or MOSFET, and a bidirectional or anti-parallel diode to provide the bidirectional conduction ability to the switch. For most loads, there are an inductive component, and for inductive loads, there is no way to interrupt the current suddenly. So, for example, if the switch S4 is closed, the returning current into phase A find an alternate instantaneous path through D1. This is why you provide anti-parallel diodes for these switches. Ultimately, each switch can be represented as a normal single-pole, single-through switch to provide bidirectional current carrying capability, as we see in this diagram. Each phase switch is replaced by one ST switch, S1, S3, S5. These are the 6 switches, and this is the load. Further information is needed here about the switching nature of this arrangement of switches. Normally, if all the 6 switches are open, we get no useful output. The load is completely isolated. So this is a trivial case. And for the other cases, there is no way to switch on S1 and S2, the upper and lower switch, in any of the 3 arms simultaneously, because this will result in shoot through or short circuit on the DC link capacitor. So this case also is excluded. If we exclude these states, we got only the possibility to switch either the upper switch or the lower switch. And if we switch the upper switch on the load, the VDC is connected to the load terminal, and if we connect or switch on the lower switch, minus VDC is applied to the phase or the load terminal A or B or C as well. So for each arm, we have only 2 conduction states, either the upper or the lower. We call this mode of switching, a complementary switching of upper and lower switches. So we have now two states to the power 3, which are 3 arms. Then we get all in all 8 switching states. So the arrangement also can be further simplified in this form, where we replace the 2 switches because we know that either the upper or the lower is on, and in between we can get a case where none of the 2 switches is conducting, and we will see why we need this case as well. So the 3 phases or the 3 arms are further simplified into this form, where one single pole double through switch is existing between the load and the DC source. So if we try to detail all the switching states, we will give, if the switch is in the upper position, then we will give a notation of 1 to the conduction state. If it is connected to the lower pole, then we will give 0 to this phase. So we can get combinations of 0 ones for all the 8 states that we say that these are the useful possible states for this topology. The simplified presentation introduced in this previous slide tells us more about the nature of switching required for upper and lower switches in each arm. It is complementary switching, since in practice no power electronics switch can change its state instantly, and all switches have longer turn of time than its turn on time. This is a characteristic of power electronic switches. So a possibility of non-intentional shoot-through is high unless an idle time is inserted between the edges of the complementary pulses to avoid simultaneous conduction. During this idle time, both switches receive off command, and this time is called dead time or dead band. Actually, this dead time or dead band make some distortion in the linearity of the 2 level inverters, but this is not the scope of this tutorial. To get a representation of the space vectors associated with these 8 states, we will give an example. For example, the switching combination 1, 0, 0, where 1 is upper switch A is connected to the positive rail, P is 0, meaning B is connected to the negative rail, and C is 0, C is connected to the negative rail. So this can be further simplified according to circuit theory, that to have a voltage DC applied to an equivalent resistance of Z plus Z by 2, because these are 2 parallel branches. The equivalent of them is Z by 2. So the total impedance is 3Z by 2, and the current is 2 VDC by 3Z. So if we want to get the current, the voltage across the phase A, VAN, we will get a voltage of 2 by 3 VDC. And for each of the phases P and C, we get a voltage equal minus VDC by 3. If we try to draw these small vectors or these individual vectors on the vector diagram, as we see in the second slide, this is the phase A, magnitude of 2 by 3 VDC, and its angle is 0. And phase B is coming with phase shift of 120 degree. Phase C after that is 120 degree lagging behind phase C. So this is VAN. VBN is negative, so we draw it in the opposite direction with 1 by 3 multiplied by DC, VDC, and VCN also as well in the opposite direction of the positive phase C with magnitude of VDC divided by 3. The enclosed angle here is 60 degrees, and the component in this direction is VDC by 6, VDC, which is VDC by 3 multiplied by cosine 60 degrees. This will result in VDC by 6. And also for VBN, we get a component in the same direction as VAN with VDC by 6. So the whole space vector, don't forget that the vertical components cancel each other due to VCN and VBN. So the resultant space vector is V1 with magnitude VDC and is aligned with the 0 direction. So this is the first diagonal of the hexagon, which is representing the conduction state 1, 0, 0. The same work can be repeated with V2, 1, 1, 0. We will get the resultant vector as V2, and this angle is 60. The same can be repeated with this conduction sequence. You can also draw the circuit, simplify the circuit, get the individual phase voltage, get the resultant, and we draw it. We'll find that it make an angle with 120 degree with V1 direction and with magnitude VDC. Please note here that the maximum phase voltage that is available from a given space vector, this is the given space vector whose magnitude is VDC, the maximum phase voltage obtained out of VDC in this case is 2 by 3 multiplied by VDC. We will need this piece of information later on. So now we understand what this shape stands for. This is a hexagon, and the diagonals of the hexagon is presenting the vectors or the space vectors resulting from the different combination of conduction states of each arm. And these vectors, space vectors, have magnitudes of VDC, and of course we need to drive any three-phase load or motor to a smoothly rotating reference voltage space vector. Look, if we just apply the first combination, then after some time we give the second combination, then after some time we give the third combination, we will get a jumping space vector applied across the load or the machine. And this cannot be sinusoidal waveform, of course. To get a smoothly or sinusoidal change of phase voltage across the load, we need to have a space vector that is controlled in magnitude, controlled in position, and controlled in the speed by which it rotates. But let us conclude about this shape now, the hexagon. We have 6 active vectors, V1, V2, V3, V4, V5, V6, and 2 zero vectors or null vectors, which is V0 and V7. V0 is 0, 0, 0. All the switches or all the switches are connected to the negative rail, lower switches, and the other one, all the positive switches are connected to the positive rail. Each one of these give us 0 vector. The other vectors, the active vector is V1 through V6. So what we need now, it is evident that applying simple switching operation on the inverter can only generate a jumping space vector. Each jump is of 60-degree span and of fixed magnitude VDC. But generating a three-phase set of voltages requires a smoothly rotating space vector, as shown in slide 2, that can be controlled in terms of magnitudes, position, and speed of rotation, angular displacement when time is incremented. To reach this objective, pulse width modulation is used. Pulse width modulation is a very known concept since a very old time. It is based on the concept that if we apply a pulse where the available voltage is switched on for some time during the pulse and off during the remaining time of the pulse, then the load will see an effective voltage equal the average voltage during this pulse period or pulse time. So for example, we give here 2 examples. We have available voltage of 9 voltage, and we apply this 9 voltage for 50% of the duration. We call this 50% the duty ratio. So if we apply 50% of the duty, we get 4.5 voltage out of the 9 voltage. This is the voltage which is effectively seen by the load. Another example, if we apply only 25% of the 9 voltage available, we get 2.25 voltage applied to the load terminal. The same concept can be used to apply a smoothly rotating space vector on a 3-phase load by the 2-level inverter described earlier. For an arbitrary desired reference space vector like V out, this one, look for this one, it is possible to decompose it to two equivalent vectors, two enclosing vectors, small vectors, V1 and in this direction, V2. To get V1, the small, from V1, the grand, we can apply the pulse width modulation concept, where the ratio of V1 to V2 will equal T1 to TZ, or to the pulse width modulation period. So we can get these two times, T1 and T2, in the diagram. The small vector V1 can be realized from the main vector V1 by pulse width modulation in this way. V1 by V1 equal T1 by TZ, and similarly V2, small one here, by V2, the grand one, equals T2 by TZ, where TZ is the pulse width modulation period. This means that a switching pattern 100 is to be maintained for a duration of T1, and a switching pattern of 110, look, 100 is V1, will be maintained for duration of T1, and the other vector 110 will be maintained for a duration of T2. The rest of the pulse width period will be applied V0, the null vectors, or V7, 111 or 000 can be applied. Then effectively the load will feel or will get the sense of this exact space vector magnitude and angle. Back to the maximum achievable space vector magnitude. It can be seen that the maximum achievable space vector length using this space vector pulse width modulation is equal to the radius of the circle enclosed in the hexagon. Recalling that the magnitude of any of the 6 active vectors is VDC, it can be deduced from the hexagon geometry that the radius of the enclosed circle is VDC, VDC multiplied by square root of 3 divided by 2. Therefore, the maximum space vector magnitude achievable with space vector pulse width modulation is square root of 3 multiplied by VDC and divided by 2. And this can give a maximum phase to neutral voltage of 2 by 3. Please refer to the freehand sketched slide. We say that the maximum phase voltage is 2 by 3 multiplied by the space vector magnitude. This is the maximum achievable space vector magnitude. And to get out the phase value, we multiply it by 2 by 3. This will give us VDC by square root of 3. And the last point is important in enforcing controller saturation limits to achieve this value, so that overmodulation is avoided. To keep the linearity of the power stage, we need to enforce this saturation limit to the V alpha, V beta controllers, which otherwise they will ask the inverter to produce voltage that is beyond its capability. A primary knowledge of VDC, magnitude of the desired space vector, angle of the desired space vector theta, pulse width modulation period, let us call it TS, is needed. This is all what we need to make the switching of the two-level algorithm. There is some steps that we have to follow to realize this switching algorithm. First one is to find the sector from 1 to 6 enclosing the desired space vector to identify the adjacent vectors. Let us look back to the slide here. In each sector, this is 1, 2, 3, 4, 5, 6. We say that we will realize any desired vector in any sector of these sectors by the two enclosing vectors. In this case of sector 1 is V1 and V2. In the case of sector 2, they are V2 and V3. We will call them also for sector 2, V1 and V2. Always V1 will be to the right of the desired space vector, and V2 will be to the left of the desired space vector. And the same concept will be applied. So the first step we need is to find the sector to point to the desired adjacent space vectors. Then we need to decompose the desired space vector into two equivalent components aligned with the enclosing diagonals of the hexagon to determine the small V1 and V2. if we got V1 and V2, the small vectors, and divided by V1 and V2, the grand vectors, then we can get the times T1 and T2. And by subtracting their summation from TS, we get the T0, the dead vectors or the null vectors time. Also, we need a mechanism to arrange the sequence of applying or transition between the desired states, because recall that we say we will apply V1 for a certain duration, which is T1, and V2 for a certain duration, which is T2. So for these two durations, we have two different vectors. We need some method to transfer from each state to the other, so that the minimum of switching operation is performed on the inverter. Because the farther that, or the more we switch the inverter, the more we cause power losses due to switching power. And this, of course, will reduce the efficiency of the inverter. In most applications of inverters, controllers are computing the desired space vector in terms of its stationary two reference frame components, V alpha and V beta. Therefore, in this presentation, we will streamline all our calculations using the available presentation of the space vector, i.e. using V alpha and V beta. So find sector number using V alpha and V beta. Please look at this representation. This is the axis of the alpha voltage, and this is the axis of the beta voltage. Look, simply, if V beta is positive, then we have a possibility of either these sectors 1 or 2 or 3. If V beta is negative, then we have possibility for either 4 or 5 or 6 sectors. For alpha positive, we tighten our choices to either 2 or 1 or 6 or 5. For V alpha negative, we also have other consideration that the space vector is lying into sector 2 or 3 or 4 or 5. So we need a certain condition to tighten the selection to say that we exactly lie in sector 1 or 2 or 3 or 4. According to the previously mentioned logic, we are still not able to isolate the sectors 1 from 2 or 2 from 3. Look, this triangle. This is V beta, and this is V beta by square root of 3. This is 30 degree. So look, if this magnitude is greater than for V alpha is greater than V beta by square root of 3, then this reference vector will be in sector 1, of course, because the resultant will have an angle that is less than 60 here. So the vector will be located in sector 1. But if V alpha is shorter than this magnitude, V beta by square root of 3, we talk about magnitudes, not magnitude with sign minus or absolute magnitude. So if V alpha is shorter than V beta by square root of 3, then the angle will be greater than 60 and the vector will lie in sector 2. The same applies here. If we turned this or mirrored this rectangle in this side, either the space vector in 3 or in 2, based on the comparison of V alpha and the V beta by square root of 3 magnitude. So there are simple logic conditions that will tell us where we exactly can locate the desired space vector. This is what we included in this table. We check for V beta for polarity, V alpha for polarity, and we check the magnitudes of V beta divided by square root of 3, compare it with V magnitude of V alpha. So these conditions are translated directly into the sector number. And as we say, we have 8 states from 0 to 7. 0 and 7 are the null states, and the active states is 1 through 6, and these are the sector numbers. There is a very simple block in MATLAB, in SIMULINK, which can directly translate the logic in this table. If you see this table, these are simply binary inputs arranged like binary inputs 000, 100, 010, 110, 001, and so they are arranged like a binary counting of 3 bits. And exactly this combinatorial logic looks at the conditions, which are arranged as binary combination of 3 bits. And for each count, a binary count, it gives a number, a predefined number. This predefined number is stated in this column. This is what we give the block. The block is given this sequence 5, 4, 5, 6, 2, 3, 2, 1, and the block itself check for the logic conditions. And based on the logic conditions, it gives the sector number. So we got the sector number, and once sector has been identified, decomposing the alpha beta vectors into V1 and V2 vectors is straightforward from principles of geometry. If any one of you has a sector and the desired reference is located inside a sector, then using V alpha and V beta coordinates of the desired vector is very simple to decompose V alpha and V beta into V1 and V2, where V1 is the space vector, which represent a diagonal of the hexagon that is taken from the sector number. For example, V1 can be V1 or can be V2 if we are in sector 2, and V2 can be V3 if we are in sector 2, and so on. Look at the hexagon for this. All what we need for this is to make some arrangement for V alpha and V beta. The equation, we write down the equations, and these equations is driven into multi-port switch composed of 6 selections, and these selections are activated with a sector number, which is calculated from the previous block. Many implementations can be given to this part, whatever you like. This is like a switch case statement, for example. Calculating T1 and T2, recalling that maximum achievable space vector is square root of 3 multiplied by VDC over 2, which corresponds to a pulse duration of full TS. So this is the VDC. We multiply it by square root of T by 2, divided by 2. And for each one of V1 and V2, we will divide, look this. We will divide, this is the BWM period, multiplied by the division of V1 over this amount. And V2, the same, is divided by this amount. And this division gives the ratio of BWM that should be assigned to V1 or V2, which are T1 or T2. Look, we get here the summation of T1 or T2, because if you forget for some reason to enforce a saturation limit for the controllers, and they ask for voltage that is beyond the capability of the inverter, then these times T1 and T2, the summation of them can exceed the pulse width modulation period. Then we need to rescale them or to rearrange them to maintain the ratio, to maintain the ratio between them and be enclosed or constrained by TS. So this is what we are making here. We get the resulting TS and we divide TS by the resulting TS. And if this amount, if this condition is true, that TS is less than resulting TS, then it means that we're asking for a longer BWM period. So then in this case, we need to correct the direct T1 and direct T2 by the ratio of TS over the resulting TS. Otherwise, we directly give out the direct T1 and T2. This switch is controlling this situation. If the correct situation is true, then we get the corrected T1 and T2. The corrected T1 and T2 is produced by multiplication of this ratio TS by the resulting TS, multiplying it by direct T1 and multiplying it by direct T2. This gives us the corrected T1 and T2. If the correct signal is true, then we get this corrected T1 and T2 out. If it is false, this means that nothing is wrong. We're asking for voltage that is within the capability of the inverter, and we will give T1 and T2 that are directly estimated or calculated from this calculation logic. Now we need a mechanism to assure minimum switching operations per leg. The mechanism depends on selecting the sequence of applying the active vectors and the zero vectors for the pre-found durations, so that minimum switching operations per phase are achieved to reduce switching losses to as minimum as possible, which is actually 2 operations for each VWM cycle. Noting that T0 equal Ts, the switching period, minus T1 minus T2, which are the duration of the active vectors. Look, this is the way in which we apply this mechanism. We draw A, P, C phases. These are the phases. Here we represent the status of the upper switch, okay? For example, in sector 1, if the V out is in sector 1, we need to apply V1 and V2, or for which time V1 and V2? For T1 and T2, okay. But which one should be applied first? Is T1 or T2? Look, this here 1, this here 0, this here 0. Where we get this 1, 0, 0? From the vector V1, 1, 0, 0. And the time for T2 is 1, 1, 0. From where we get this sequence 1, 1, 0? From V2, 1, 1, 0. Okay. Look, if we exchange the positions of applying V1 and V2, we will get this small pulse here, and this will be low. So we will make a switching on here, then switching off here, then switching on here, and so on. And this will distort this arrangement, will give us minimum unnecessary switching per phase. So the optimum choice here is to apply first T1, but followed by T2, and the time T0 for the null vectors is divided into 3 slots like this. 1/4 of the dead time, 1/4, of the null vector time is to the left, and 1/4 is to the right, and half of this time is in the middle. This arrangement gives us what we call center-aligned pulse width modulation. The same can be also made if we choose right-aligned or left-aligned pulse width modulation. But let us consider this case, center-aligned pulse width modulation. So look at this. It means that we need to maintain the switch A on for whole of this time. Look, if you try to say the total time for which the switch A for upper switch for phase A is turned on, it equals T1, because we have 2 portions, T1 by 2, and T2, we have 2 portions, T2 by 2. So their sum is T1 plus T2. And also we have T0 divided by 2. So we can simply get the law for switching the switch A. We call that the A minus is the complementary of this pulse. So if we get this, the other one is obtained directly. And in most DSPs, the controller itself inserts the dead time between the switching and the complementary, the switching signal and its complementary. For example, for phase B, to get the law of dwell time for phase B, simply it is T2, 2 halves, T2 plus T0 over 2. And for phase C, it's only half the T0, half the null time vector. So in this way, we make a very wise sequence where each phase has only 2 transitions. This is 1 transition from 0 to 1 and 1 transition from 1 to 0 in phase A. In phase B, the same story. 1 transition 0 to 1 and 1 transition 1 to 0. The same is phase C also. Go to another sector, sector 2. Sector 2, we have this vector 1, 1, 0 and 1, 0, 0, 1, 0. 1, 1, 0 and 0, 1, 0. So the first one, 1, 1, 0, is devoted to T1. T1 is the time to maintain this this vector V2, 1, 1, 0. Look, here we write down V2, and we write down here the other vector, which stands for V2, is V3 here, V3. So we alternate between V3 and V2 in this way. You see here a contiguous pulse, 2 transitions only in phase A, 2 transitions in phase B. We don't have many possibilities. We have only 2 possibilities, either to put V3 here or V3 here. So you can try it yourself, and only the selection or only the choice that will result in a contiguous pulse for phase A, a contiguous pulse for phase B, and also a contiguous pulse for phase C is a right selection. We repeat this for all of these 6 sectors, and we can write down in a table the dwell time law for phase A, B, C, the upper switch of each arm. Okay, and you can use any implementation to apply this information or this control law to phase A and phase B and phase C. Here, what I made is to prepare some calculation. For example, T1, T2, T0 is the summation of T1 and T2 is the summation of the quantities T2 and pulse width modulation period to derive T0 by 2. And for example, this is T1 plus T2 plus T0 over 2. And based on the sector, I apply the law for TA, for TB. These are the 6 laws for TB. These are the 6 laws for TC. And based on the sector number, I provide the time, the dwell time for the upper switch in each arm. Recall that this is time, and if you want to get a duty ratio, we divide this time by the pulse width modulation period TS. And to check if your calculation is correct or not, this is a typical duty ratio profile of the 3 phases. As you see, it moves between 0 and 1, and it takes this this profile, and this profile can simply be deduced from it that it's a sinusoidal waveform added to it a third harmonic component. And by the way, this also represents the phase voltage in 2-level inverters, but in this case, the phase voltage takes the form of bipolar signal, not unipolar, moving between 0 and 1. It's symmetrical in the case of phase voltage. The case of the line voltage, which is 2 phases subtracted from each other. For example, VAB, line AB is VA minus VB. Then the third harmonic component cancel each other, and we get line voltage is perfect sinusoid. Important to note that in 2-level inverter topology controlled by space vector pulse width modulation, each PWM cycle involves 6 state transitions or switching operations, 2 per each leg. A switch turned from on to off has to block the full DC link voltage, and hence dV by dt stress are high. Some power electronic switches can be turned on without gating signal if dV by dt exceeds certain threshold, which can also damage the switch. Therefore, snapper devices has to be considered in this application. How DSPs and microcontrollers generate pulse width modulation? Edge-aligned modes and center-aligned modes are available in most DSPs and micros. Simply, the DSP has some peripherals to count and can be programmed to count in up-down mode like this. And the duty or the time for on is pre-latched in some registers, and the count is always compared to the value in these registers, and when the count reaches the preset value for duty, then the a digital bit is turned from off to on. So we get finally a pulse, and on the other channel we get the complementary of this pulse, and there is always a dead time module which insert for each leading edge some amount of pre-programmed duration, which is the dead time as explained earlier. Most power electronics, as we say, change its state within a finite time and not instantly. Indeed, the switches turn off slower than they're turning on. If sharp transition is in complementary mode are allowed through the shoot through will result short circuit on the DC bus, which will destroy the ARM switches and also maybe damaging the DC source. This is why a delay is inserted between the trailing edges of the turning off switch signal and the leading edge, trailing edge, sorry, here there is a syntax error here, and the leading edge of the turning on switching signal of any two complementary switches. And this is by default a hardware built module inside most DSPs and microcontrollers. Here is a nice topic that we have learned during our work in one of the projects where we need an active low signal to drive the switches, because the driving circuit needs an active low signal. So we thought that if we got the signal for the bottom switch to drive the upper switch, nothing will happen and we can satisfy the requirement of the driving circuit. But this is completely false. Look, this is a switching signal generated by the DSP for an active high gating pulse, for active high driving circuit. Then this is a dead time, as you see. Here is clear band where both switches are off. Okay, but for the driving circuit, if it receives the inverted signal, I mean, if you put DCS3 in place of DCS-T1, and we take this signal and we say this will be used to drive the upper switch, and this will be used to drive the lower switch to meet the requirement of active low switching. This is what happens. The driving circuit will take this pulse, as you see. It is driven by active low signal. So all of this span where active low signal is used to generate a pulse for turning on the upper transistor. And all this blank, all this off duration will be used to generate the driving signal, the gate signal of the lower switch. Look what happens. Here, the dead band is not a dead band. There is overlap in conduction between upper switch and lower switch. Even though the DCS or the DSP has generated already the dead band, but this concept is invalid and it should be never used to replace inverting stage ahead of the active low driving circuit. Thanks for your attention. And this is for time being is enough to switch to the remaining of the tutorial, which is 3-level inverter topology. And we will make a short break and then resume our lecture. Hello, everybody. We come back to the tutorial. There's some motivation for more multi-level topologies. For example, in 2-level configuration, harmonic distortion in currents can be reduced by increasing switching frequency, but increasing switching frequency increases inverter losses and reduce efficiency. Nevertheless, in high power applications, recommended switching frequency is almost below 1 kHz to restrict switching power losses. However, the need for reducing total harmonic distortion is still valid. Indeed, DC link voltage in 2-level is more restricted by the power electronic device rating because it has to block the full DC link voltage. Otherwise, devices has to be connected in series to raise the resultant voltage blocking capability. This is also problematic because it needs special voltage balancing techniques that are complex, expensive, and compromise inverter reliability. These are the motivations behind introducing multi-level inverter topologies, as we will see later how these issues are handled. In three-level inverter topologies, there are some old configuration and there are some modern configuration. Nowadays, there is what we call modular multi-level converter, which can give any number of levels you desire. But for all the implementation, there are two typical three-level topologies as described by this slide. The first one is a neutral point clamped configuration where we have 6 more diodes in the current path. As you see here, these two diodes, these two diodes, these two diodes. These two diodes are in the current path and they carry current and they result in conduction losses, elevated conduction losses. And the other topology is a T-type, which has less devices and therefore it is more efficient. The main difference is that P-type has less conduction losses and certainly higher efficiency. Similar to what we have done in two-level inverter topology, we need here to find the useful and the prohibited switching combinations. Any simultaneous switching that can lead to shorting the DC bus or one of its halves is prohibited. For example, T1 with T4 or T1 with T2 with T3, etc. Please refer to the inverter topology. Look, for this, for example, T1 and T4, if switched on together, they will make a short across P and N terminals of the DC bus. If, for example, T1, T3, T2 are switched on, or T1 and T2, T3 together are switched on, then we will have also a short pass on B with O. And for the lower part, if this transistor is turned on, the diode will allow current flow if this switch T4 is turned on simultaneously. So T2 with T4 is forbidden to conduct together. Okay. T2, yes, T2 with T4, because it will result in a short pass for the lower DC link half. So these are forbidden states, and the algorithm itself should take care that none of these switching combination will occur during operation. And the other case, which is not useful, that all switches are open because the load is isolated, and this is not a useful combination anyway. So the switching states of a phase, if we look, for example, at this phase, this single phase, connected to a load, and this is a neutral point. This is the midpoint of the VDC. These are the switches, our switches Q1, Q3, Q3, Q2, Q4, because as we explained in the two-level, each switch has anti-parallel diode connected with it. It can be replaced by a switch like this, which can carry current in the two directions. Look, for example, to apply VDC by 2 on the load, we need to switch on Q1 only, Q1, and the other switches receive 0, 0, 0. To connect the load to the O point, we need only to connect Q2 and Q3. Look, why Q2 and Q3? We need to go back here. Q2 and Q3, because each single transistor is not able, alone, to carry the current in both directions. For example, T3 can, with this diode, with this D2, can carry the current in this direction, and T2 with D3 can carry the current in this direction. So in all possible directions of current, to apply a voltage of 0 on a phase like A or B or C, the two switches should be switched on. The two horizontal arm switches should be turned on. So this is the second voltage possibility for a phase terminal. The third one is if we close the lower switch like that, then we will apply the negative rail voltage on the load. This is minus VDC over 2 if we respect this voltage of, if we refer this voltage to the point O. And this is what is written here. Phase voltage with respect to O. Okay? So it's clear that any of Q1 or Q4, look at this, Q1 and Q4, Q1 and Q4, either they are complementary or I2 that both of them are switched off. Okay, it's clear that any of Q1, Q4 is required to block VDC over 2. Because if we switch it on, it applies VDC over 2. If you switch it off, it will block this voltage as well. So when it is switched between B and 0, look at this. If you switch it between B and 0, or between 0 and B, or between 0 and N, between N and 0, all of these transitions will make the switch stressed by VDC over 2. But if you moved from B to N or N to B, then the switch will have a stress of VDC. So also the algorithm should not allow direct transitions between B and N or N and B. Okay, this is why the switches of this topology, 3-level topology, is rated only to withstand half of the DC link voltage. And this is sufficient for safe operation of this topology. This is one possibility for switching, of course. There is another possibility, and this other possibility add some advantage, as we will see in the switching pattern. In this modified switching, keeping Q2 on during Q1 conduction will not result in current flow in bus OA, but will reduce switching losses in Q2 and also voltage stress on it. Look for this. The current path is in this way, in this direction, okay? And switching this switch on will not make any contribution to the load voltage, actually. It will be equal also to VDC by 2. But if it maintained on, then when we need to apply voltage 0, the Q3 need to be switched on with Q2. And all what we need to switch in this case is Q3. So Q2 is always on, Q3 will apply the voltage 0. So minimum switching is needed for Q2 in this case. This is clear in the next slide. Also, it applies to the Q3 with Q4. Q3 with Q4. As we see here, Q3 with Q4. So we have either Q1 with Q2, switch it on together, or Q3 or and Q4 to switch it on together to give minus VDC, or Q2 and Q3 switch it on together to give 0 voltage. The same function explained for Q2 to be maintained on with Q1 is true also for Q4 to be maintained on Q3, sorry, to be maintained on with Q4. Because if this Q3 is maintained with Q4, Q4 in this case is drawing the current from the load into the negative rail. And in this case, Q3 will not allow any current flow in this path because Q2 is off. But if we want to put a 0 voltage here, just we switch on Q2 and off Q4. Look for this nice part. As you see, Q1 and Q3 is always complementary. Q4 and Q2 are always complementary. Look at the second row. Q4 and Q2. Q3 and Q1. These are 0, 1, these are 1, 0. In this case as well. So Q1 and Q3 are complementary, Q4 and Q2 are complementary as well. In all the possibilities that we have. Here also Q3 and Q1, Q4 and Q2. So if we could get the time, the on time for any of these two switches, Q1 and Q2, that will be sufficient to switch the whole arc, because the other two signals are complementary of these two switch states. So what we search for from now on is the on time for Q1 and for Q2. Q3 and Q4 will be reduced as complementary of the other switches. Okay. This is what we call the optimized switching or the modified switch. The first case, as you see, we have to always switch on and off very fast, Q2 and Q3, to give the zero voltage. Because remember or recall that we always move between VDC or P and N and zero, and N and zero. So these two switches are always in a switching state, But look, in the other case, we maintain the switch on the whole period, all this point. So Q2 and Q3, the only one which modulate, which will apply the zero voltage is Q3. Q2 is on the whole time. Here also is on the whole time, so Q3 will give the zero voltage for this period. These are the switching case also for Q1. The other one, you will see that the other one also here in this duration is on the whole time. So Q4 will give be served by Q3, but by Q2 with Q3 to apply the zero voltage. What we want to briefly say here is that this modified switching gives more efficient operation because it keeps Q2 and Q3 at as low as possible switching during the inverter operation. Back to this table, we designate this voltage by these conduction states by B, 0, and N. So each R will have only these three useful states: P, O, useful and allowed, P, O, N, P, O, N. And as we say, we have to confine the transition so that P to N or N to B is not allowed. Okay. So for three arms, each arm has three possibilities. We have 3 to the power of 3 states, possible states. This is 27 possible combinations, if you see here. And we can put these combinations in a table like this. These are 27 states, and these are the designations given to each state. And for phase A, phase B, phase C, the letter describing the conduction state is given here. And recall that this letter is corresponding to definite conduction state for each of the 4 switches. For B is Q1 is on, Q2 is on, Q3 is off, Q4 is off. Okay, for each symbol of these, we have very definite conduction state description for each of the 4 switches of each phase. Okay, so if I say to you, NON describe the 12 conduction state of the inverter, you can say that for phase A, this N means that phase A is 0, 0, 1, 1. Okay, and phase the other phase B and C also can be extracted from the table, which are conduction states of the switches for each of these 2 phases. Okay. Then to express the voltage with respect to the point N, look, we need to define the following switching function: Sx, switching function x, and equal this. We give 3 combinations or 3 states, as we say, we have B and 0 and N, and each state will give it a number 2, 1, 0. The relationship between single phase output voltage with respect to O, this is the midpoint, and switching function is as follows: UAO equal SA minus 1. Remember that this combination is for each phase. I mean, this state is defined for a phase, and this phase is X. So we have UAO, then we put SA, the switching function of phase A. If it is 2, we get some value. If it is 1, we get some value of the voltage. If it is 0, we get some value for the voltage across the phase. Okay? So, and if you review the value written in the table, you will find it for this combination of switches, we get VDC by 2. For this combination, we get minus VDC by 2. For this combination, we get 1 minus 1, which is 0. It is 0 voltage. Okay? So this is complying with what is written in the previous slides. Now, we want to calculate the phase voltage with respect to the neutral point of the load, not to the midpoint of the DC. And for this, we write down the loop equation for the 3 phases in this way. It's inductive load, LdIA by dt plus RIA equal EA minus UAO plus UOM plus UMN. Okay, recall that this is the electromotive force in phase A and in phase B and in phase C. Okay, phase A, phase B, phase C. And this is minus the voltage applied by the inverter, which is UA referred to the point O plus UO referred to the point M plus UM referred to the point N. Okay, simply we can get UON by combining these 3 equations, and you will find that UON equal UDC by 6 multiplied by the summation of SX minus 1. Meaning that for each combination for a phase, we can get the UON for this combination and for this phase. Okay, recalling that this is a 3-wire system and balanced, so the EA plus EB plus EC equals 0, IA plus IB plus IC equals 0, and this can help us in moving from this equation to this equation. To get a clear interception of the O and M and N, look, this is the N, the neutral point of the load, the motor or the grid, and this is the O, the midpoint of the DC link, and this is the point M. We say OM, and there is a voltage between M and N. And what in the equation we got the voltage O to N. Okay, the voltage O to N. And using this voltage O to N, we can get the phase voltage A and B and C referred to the midpoint of the to the neutral point of the load, which is UAN, UBN, UCN. If you subtract these voltage, we can express UA with respect to N and UB with respect to N. Okay. And after getting the ABC voltage, we can express them in the form of V alpha, V beta, according to the well-known transformation matrix like this. Note that the scaling factor should be considered, if you put it here, it should be considered in the rest of the analysis. Okay. So this is what is explained in the previous slide. SA, SP, SC is a switching function associated with each pattern, conduction state pattern, B, B, B. These are the 27 conduction states or conduction state combinations. And this is the switching function. If we apply the switching function, we get UA, UBO, UCO, referred to the midpoint of the DC. And UON, we get it from the equation, equation 4, this one, summation of SX. SX means SA plus SP plus SC minus 1. Okay. So we get those summation minus 1 divided by 6 multiplied by VDC. Okay. So you can get UON, and if you say UAO minus UON, it will give you the UA with respect to N, which This is the value which we need to know. UAN, UBN, UCN. These are the three-phase voltage referred to the neutral point of the load or the grid. Applying Clark's transformation, we get V alpha and V beta component. This is straightforward. And V alpha and V beta component, we can get them as a space vector representation. The square root of V alpha squared plus V beta squared will give us the square voltage magnitude, and attend to V beta divided by V alpha will give us the angle of the space vector, of the resulting space vector. Very fine. So using these last two columns, we can construct the following space vector diagram. This one. Simply, each conduction pattern or conduction state combination can have a magnitude and angle. We draw all of these combinations in a one diagram as magnitudes and angles. Okay. Just we want to inspect the table for something. We can find 27 space vectors. Of these vectors, we will have 3 vectors of zero magnitude. We call them the zero vectors, PB, OO, and NN. Okay, look, OO, PB, NN. Okay, the first 3. And of course, this will give us a point, null vector. Okay, then we will have other 12 vectors, like as we see. These 12 vectors are small vectors. Each one has a magnitude of UDC by 3. They can be grouped in 6 pairs of redundant vectors as follows: POO, ONN, PBO, OON, OBO, NON, OBB, NOO, OOB, NNO, and BOB, ONO. The tips of these vectors are located at the 6 vertices of the inner hexagon in space vector diagram. These vectors are colored with light orange color in the table. And these pairs are displaced by 60 degrees. Okay, light yellow color, as you see here. These are 12 vectors, and if you draw them, you will find each two coincide with each other. Okay, we will see them on the diagram. There are also 6 medium vectors. The magnitude of each vector is UDC by square root of 3, and this medium-sized group of vectors includes PON, OPN, NBO, NOB, ONB, and PNO. This group is colored in the table with dark orange. The vectors of this group are also displaced 60 degrees with each other and 30 degrees with the nearest small vector. We can go back to the table. See, dark yellow or orange, this one. And as you see, you will see them on the figure later. And we have finally 6 other vectors, the red one, which is the last group of vectors, which is composed of 6 large vectors of magnitude 2 UDC by 3, and they coincide with the small vector pairs. This group is colored in red in table 3. Okay. These are the 12 vectors. Each one has a redundant one. And these are the medium vectors. And these are the large vectors, which are lined with the small vectors. This is the small vector group. And this is how we got this space vector diagram. Okay. Of course, each tip or each vertex of these, we can have its coordinates in alpha beta plane. Okay, the largest achievable space vector magnitude also is a question here, and it's clear that the maximum achievable space vector magnitude is the radius of the inner circle enclosed by the outer hexagon. This radius is equal to the length of any of the medium vectors, which is UDC by square root of 3, noting that we used a 2 by 3 scaling factor in Clark's transform, and that we constructed the space vector using the V alpha and beta obtained from Clark's transform. Therefore, the correct space vector maximum length is, we multiply by the inverse of this ratio, 3 by 2 multiplied by UDC over square root of 3 will give us square root of 3 multiplied by UDC over 2. The maximum attainable phase to neutral voltage is recall what we have done in the freehand sketch slide in the first presentation. It is equal to 2/3 of the maximum space vector length. So the maximum phase voltage achievable with the three-level topology is also UDC by square root of 3, and this is the limit that we have to enforce as saturation limit to the controllers, which are computing alpha and beta voltage. Where to go from here? Various voltage averaging techniques can be used to realize a given reference space vector, e.g. nearest three vectors, whereas 6 hexagons and 4 sub-triangles in each hexa are used to locate the nearest 3 vectors. Many methods, in fact, and this can also be traced in literature. Another straightforward technique is built on the knowledge gained from two-level space vector pulse width modulation generation. This is why we review briefly the space vector modulation of two levels. The whole space vector hexagon is divided into 6 sub-hexagons, and each sub-hexa will be divided into 6 subsectors in analogy to the two-level case. This technique will be used in this tutorial. Look, this is a ground space vector hexagon, and we will identify 6 small sub-hexagons in this way. This is number 1, this is number 2, this is number 3, this is number 4, this is number 5, this is number 6. If you look carefully, then you will find 1 and 2 overlapping in some area, and 2 and 3 also are overlapping in some area. So finding which sub-hexa is the home for the desired space vector is a complicated task in this case. So we redefine the sub-hexa in this form. We will say that only this area is sub-hexa 1, only this area is sub-hexa 2. So you see here that there is no overlap. This is a clear area pertaining to sector or to sub-hexa 1. This is a clear area not overlapping right or left with any other sub-hexa. This is number 3, 4, 5, 6. Okay. In this case, it's easy to allocate or to locate the desired space vector sub-hexa where it is located. Okay. This simple logic is through using the phase voltage, the desired reference phase voltage, according to this logic. So using VA, VBC, VC, and comparing them with the 0 voltage will give us the sub-hexa number, and this can be implemented in a switch case statement or in a block like the combinatorial logic as we have used before. So for any of this sub-hexa, we go back. Here. For any of these sub-hexa, for example, 1, if we got a reference vector like this, reference vector is actually originating from the null point or the null vectors, which is BBB, NNN, or OOO, in any of these sub-hexa. So we'll take an example for sub-hexa number 1 and give a desired space vector that we need to realize. Then one way to go forward is to decompose this V reference in 2 components. One component is from the ground center point of the hexagon to the local center point of each sub-hexa. Okay? Please recall that the coordinate of these vertices or these crossings or these centers of the sub-hexagon can be calculated from simple geometric analysis. So to decompose this voltage, we compose it in 2 components, this one and what we call the small one. The small one is connecting between the tip of the reference space vector and the center of the local center of the sub-hexagon. Okay. So we will call this one the small vector. Please remember this name. And this one can be identified from the coordinates of this point. For any subhexa, will have a local center, and this local center have definite and known coordinates for V alpha and V beta. So this vector is entirely defined for any space, reference space vector. Only this we need to calculate. And the calculation of this also is straightforward. If we have the coordinates alpha beta for this point, and we have V alpha beta for this point, then the V alpha is simply V alpha of the V reference minus V alpha of the center. And V beta of the V reference here minus the V beta of the local center of the subhexagon. This is very clear and straightforward decomposition. So for each subhexa, have a center pole whose alpha and beta coordinates can be easily found from geometry principles. These coordinates represent the offset in alpha beta directions that can be subtracted from the alpha beta coordinates of the reference space vector to find the alpha beta coordinates of the small vector in this way. So V small vector alpha equal V alpha now is minus V alpha offset, and V small vector beta equal V beta of the reference vector minus V beta offset. These V alpha offset and V beta offset are subhexa dependent. Look at this table. For each subhexa, we can define the zero vector, the center, the local center of the subhexa. If we go to the grand subhexagon, we can identify these centers. We can also get the V1, V2, V3, V4, V5, V6 vectors. And for example, for this one, you can look at the 6 vertices, and you can look at the local point, local center to find this arrangement, POOLN. And you can also find V alpha offset and V beta offset. This is in subhexa 1. For each of one of the subhexagons, the 6 subhexagons, we can find such information. Okay. Okay. We go now to the reduction of degrees of freedom. If you look at the subhexa 1, for example, this one example, and we can apply the same concepts to the other 5 subhexagons. Okay. Look at this. The notations marked on each vertex can be extracted from the grand subhexagon. So for this one, the local center is POONN. Recall that P is a conduction state of phase A, describing the state of the 4 switches, O for phase B, O for phase C. Okay, and this marking is too much. I mean, it gives a lot of freedom to represent what we need to represent, the space vector. And one way to reduce this degrees of freedom is to look carefully at the vertices where only single combination is given. For example, in this vertex, in this and this, we can find that phase A have only B. It has no, and the center as well. We need to look at the center and the 3 single vertices, the vertices which have single combination. Look, for phase A, for example, we have only B or O. There is no N. B, 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 or O. So phase A has no N in this subhexa. Look at phase B. Phase B has either O or N, N, N. So phase B has no B, no P. Phase C, look at phase C. It is N or O, N, O. So phase C has no B. This information is written here. So we go to the other vertices and we omit the markings that is contradicting with our finding here. For example, phase A has no N, So this one should be omitted. This one, phase A has no n. Okay? Okay. Phase B has no B. This one also can be omitted here. This one also can be omitted here. No B. Okay? And the third one, phase C has no B. Phase C has no B. This one should be removed, and this one should be removed. So we are left with these markings only. Now we have only single combination bare vertex. Okay? Only the center point, or the what we used as a zero vector in two level. Now it's not actually a zero vector, but it's an active vector, because as you see, BOO is not BBB or NNN or OOO. These are active vectors. But anyway, what we applied in the case of two level can be applied also equally here. Look, we can extend this exclusion criteria to vertices 2 and 3 degrees of freedom, help us move from the leftmost hexa to the middle one. This is the point at which we stand now. Now we want to move forward to this more simplification. Okay. For example, phase A has only state B and O. B and O. So for phase A, we will give B, which is more positive than O. We will give B, wherever B is existing in phase A, the symbol 1. And for phase A also, 0, O will be given a symbol 0. Phase A. Look at phase A. Here is B for phase A is 1. O for phase A is 0. O for phase A is 0. O for phase A is 0. B for phase A is 1. B for phase A is 1. And we go to all the existing of B for phase A and O for phase A and replace them with 1 and 0. The same applies to phase B. Phase B has no B, so it has only O and N. Logically, O is more positive than N, so we will replace O with 1 and N with 0, and go to everywhere for phase B in the main hexagon, and we replace it O with 1 and N with 0. O with 1 and N with 0. For example, this N given here, it is given here 0. Okay, here N is given 0. Here N is given 0. And the same applies to phase C. Phase C has O and N and no B. So O is more positive than N. So wherever phase C has O, we will replace it with 1. Wherever phase C has N, it will be replaced with 0. Okay? After you accomplish this replacement, then you end up with a very similar hexagon to the two-level case. Okay? So there's 6 sectors, and the sectors have the same notation 1, 0, 0, like in two level. 1, 1, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0. Okay? So this is already two-level case. Okay? And we can deal with it in the same way as we deal with the two-level case. Going closer to the two-level analogy. This is what we explained in the previous slide, how to move from this to this. Okay. Now look at what we have finally developed. It's quite similar to what we used in two-level space vector path simulation. Remember that VS alpha and VS beta are now known. VS alpha is a small vector. Alpha and beta are what stand for the reference vector in the two-level case. Okay, this is what we will use here to find out the sector and the V1 and the V2 and so on. Okay, and accordingly T1 and T2. And TS, if we know TS, then we can get T0. And each subhexa of the remaining 5 can be driven to reach a similar stage with different zero vectors and vertices, of course. Of course, the other ones, you end up with something like that, but it will end up in the arrangement of like this exactly, okay? From the viewpoint of 0 and 1, the voltage, these voltages. Okay, we will take an example, subsector 1 in subhexa 1. As we say, how do we know that we are in subhexa 1, in subsector 1? This is according to the small vector alpha and beta. We use it to discriminate the sector number as exactly we used to do in the 2-level case. How do we know that we are in subhexa 1? It is described earlier in one of the slides mentioned before we reach this slide. For each subhexa of the 6 available and each subsector of the 6 available, a similar table need to be constructed and be by inspection the dwell time on time of each basic switch. Basic switches we call T1 and T2 the basic switches, T3 and T4 the complementary switches. For each phase, look at this, for each phase. So for the whole inverter, we need a total of 6 dwell time laws, 6 dwell time laws to be extracted from the logic. We use the same mechanism as we used in the 2-level case. We put the markings. The markings is what will tell us how to put 0, 1, the conduction states. For example, look at this. We put the voltage and their translation to 0, 1, this translation. We put the translation to BON symbols, and the translation to BON symbols exactly what we use to describe the conduction state here. For example, this ONN means that for phase A, O is described by this conduction state, T1 0, T2 1, T3 1, T4 0, O. For phase B, N, this N, and N is translated to the two switches T3 and T4 on, and the others are zeros. For the phase C, N means that you have 0, 0, 1, 1. Okay? Look, the segmentation of the times V1 is applied for T1, V2 is applied T1 over 2, V2 is applied for in this area, T2 over 2. This is T naught or T0 over 2. This is T0 over 4. This is T0 over 4. Okay, this translation, where we get it? We get it from the sub-hexagon marking. As you see here, we simplified it, passing by 2 stages. This stage has the PON marking, and this stage has the 0, 1 markings. And we use V1 and V2, the markings of V1 and V2, using the 0, 1 notation here, using the OBN notation here, and we put the times as we used in the 2-level case in this row. Okay. Now, also there is 2 only options to put V1 and V2. To put V1 and V2, either to put V1 in this column and V2 in this column, or V2 in the 2nd column and V1 in the 3rd column. And these possibilities, we only choose the one which give us minimum transition per phase. And we found that the minimum transition per phase is resulting from this arrangement, okay? So if I ask you, please derive the law for switch 1A, switch T1 in phase A. You say, okay, this is on. So the whole TS period is on except for these two slots, and each of these 2 slots is 2 0 by 4. So you say T1A equal the dwell time is TS, entire TS minus TO by 2, which is TO by 4 and TO by 4. And For this one, T2, how, from where this 1 and 0 comes, as I say, from the translation of ONN, BNN, okay? For example, this PON, if you switch V2 in place of V1 and V1 in place of V2, then the shape of these pulses can be changed. And we are interested only in the shape of pulses that result in minimum transition. So look at this. This is a pulse of contiguous ones and 0, 0. This is a pulse on the entire TS. And this is the complement. This is the complement. We DSPs are producing this complement without any intervention from our side. Okay? We give only the dwell time for A, or duty ratio for A, 1A and 2A, and for 1B and 2B, for 1C and 2C. And please make sure that what we said about complementary switching of T1 and T3, they are complementary. As you see, this is 0, this is 1. And this is 1s, and they are 0s. And this is 0, and this is 1. T2 and T4 are also complementary. So for T2, it is on along the whole, the entire pulse width modulation period, and T4 is off along the entire pulse width modulation period for phase A. For phase B, you repeat the same. For phase C, you repeat the same. So you can get the pulse width modulation duty ratios for all the switches, the 6 basic switches, and the other, as we say, are complementary switches. Okay, if you repeat this for the 6 sub-hexa and the 6 sectors in each sub-hexa, you get a table like this one. In this table, you have the dwell time, and if you divide this dwell time by TS, then you get the duty ratio, which is required to derive the pulse width modulation channels in a DSP. These are the sub-hexa, this sub-sector, and these are the basic 6 switch times. Okay. Of course, we have 6 subsectors in 6 sub-hexa. This will give us 36 rows, 36 states. Okay, this is the last one, 36 states. And only a very simple operation we introduced here is that we want to decode each sub-hexa and each subsector in a one number, okay? In a one number. So this table can be populated in the same way. And to streamline our implementation, we make some coding mechanisms so that each combination of sub-hexagon and subsector can be assigned a single number like this. And this coding formula is given here. We call the resulting number a serial. And this serial is calculated from this formula. Hexagon number minus 1 multiplied by 10 plus sector number minus hexagon number minus 1 multiplied by 10 plus SN more than 11, more than or equal 11 multiplied by 4. This is a logic, simple logic and mathematical calculation that will result in 36 contiguous number representing all the possibilities of serial and sub-hexagon of subsector and sub-hexagon, where HN is the sub-hexagon number and SN is the subsector number. This formula generates the contiguous serial given in the last column of the previous table for the subsequential indicated listing of all sub-hexa sub-hectors combination. As you see in this table, this number is the serial, and it is the result of applying this formula to the combination of sub-hexa number and subsector number. Okay. Okay. So now, this is the contiguous serialization, the formula of serialization that will give us a serial sequence number, hexa number, subsector number. Okay. And if you inspect the entries in the table for the dwell time, you will find 6 unique values as follows. This one of the unique values, we call it VAL1, val1, val2, val3, val4 through val6. Okay. Hence, the previous table can be populated with val1 through val6 as shown in the next slide. Okay, this is the 36 combination. This is the vals, val1, val2. So, to recap, what we will do to reach finally this implementation is we read V alpha, V beta of the reference space vector. We find the sub-hexagon number from V alpha, V beta using the phase voltage. We convert V alpha, V beta to VA, VB, VC, and using the logic I mentioned earlier, we get the sub-hexagon number. And then we find the small vector Vs alpha minus Vs beta by subtracting the V alpha and V beta from the offset for each sub-hexa. We get the Vs alpha, V small beta. From this V small alpha and beta vectors, we can find the subsector number, and we can find V1 and V2, the small voltage V1 and V2. And if we know the BWM frequency or period, we can find T1, T2, and T0, or T8, TB, T0. And from this, we can find the vals. And from knowing the serial number, we can get the dwell time for each of the 6 basic switches. And we repeat this story as long as the space vector modulation operation is continuing. This is the SIMULINK implementation. This is the V alpha beta, and this is the hexa number. The hexa number and the V alpha beta, we get the small vector V alpha beta small. And from V alpha beta small, we get the subsector number and V1 and V2. From the information of the BWM period, we get the TA, TB, T1, TA, TB, T0, and also VDC information is needed in this stage. And from the hexa number and subsector number, we get the serial number according to the logic formula mentioned earlier. And using the serial number and the TA, TB to T0 and the information given in the large table of the 36 serials, we get the T1A, T2A, T1B, T2B, T1C, T2C. And these dwell times, if divided by the TS switching period, we get the duty ratio that is delivered to the BWM channels of the DSP. Okay. Okay. Testing the algorithm on SIMULINK using an inductive load. Look, in this test, we make an inverter, and actually it's an interesting experiment. Recall that the inverter topology is quite similar to the 2-level if we omitted or deleted or ignored the 3 horizontal arms. So if we switch the 6 switches, we can operate the inverter in 2-level mode. And if we use the whole 12 switches, we can drive the inverter in 3-level mode. So for the first half second in this graphs, we drive the inverter in 2-level mode. For the next half second or 0.005 second, we drive it in a 3-level mode. You can see even from this pulsing, from this voltage waveform per phase, that is 2-level. Here, 2-level. Here we can find 3-level, 1, 2, 3 levels. Okay. And of course, as we expected, in the 2-level, the current is having more harmonic content, and for the 3-level, the current is smoother and with less harmonic distortion. And this is the line voltage in the 2-level. This is the shade. In the 3-level, this is the shade. The problem, the bad news is that DC capacitor voltage is unbalanced, meaning that along with time, the division of the capacitor voltage, the DC voltage along the 2 capacitors, the upper and lower, is different. This is the VDC high and VDC low, higher capacitor and lower capacitor. As you see, they are diverging, and this is only a fraction of time, very small time. In 2-level case, there is no divergence because we are not connecting to the midpoints, so there is unbalanced charging and discharging of capacitor. But in the 3-level case, there will be unbalance, and this unbalance in very short period make this, and it can fully deplete the lower capacitor or the hour capacitor, so that one of the capacitor will bear the full DC voltage, which it is not rated, and the other may have a 0 voltage. This is mainly due to uneven charging and discharging of DC link upper and lower capacitor. This is a vicious cycle. More fluctuations lead to more harmonic distortion in the output and further uneven charging and discharging, which put the capacitors and power switches at great risk and deteriorate the inverter performance. Okay, and this problem, of course, need to be fixed before you use this algorithm which we have explained earlier. So additional balancing hardware, added cost and complications. Some people use this method, and therefore it's not widely used due to complications, added cost. The commonly used solution depends on exploiting the additional degree of freedom or degrees of freedom to balance the voltage, since it's observed that these redundant switching states affect the neutral point voltage oppositely. And a second method involves rearranging the time distribution between the redundant 0 voltage vectors in a way that counteract the imbalance. The good news is that our implementation lends itself easily to the application of both software methods. Figure 18, this one, and the table beside it tells us that any reference space vector in an overlapping sector can be realized using the vectors belonging to any of the 2 sub-hexa. Look at this. This is sub-hexa 1, this is sub-hexa 2, and this is the overlapping region. In the overlapping region, we have 2 sub-hexas, subsectors, sorry. For example, 2 and 3 is coinciding with 5 and 6 here in sub-hexa 2. The same applies well to sub-hexa 3. For example, 3 and 4 in sub-hexa 2 are the same as 1 and 6 in sub-hexa 3. So therefore, we can construct some table like this, where we say these are the overlapping areas. Sub-hexa 1, subsector 2 is coinciding with sub-hexa 2, subsector 6. Okay? This is why we do that. Because we need to find in all of these overlapping areas, if the space vector tip is found in any of these overlapping areas, then we can realize the desired space vector using a basic implementation and an alternative implementation. The basic implementation will use the first sub-hexa and subsector, and the alternative implementation will use the redundant one. For example, let us give an example. This one, if the space vector is here, we have a complete freedom to realize this space vector using the sub-hexa one as a native choice. Okay, and in sub-hexa 1, it can be that the space vector in sector 2, subsector 2, or we can use sub-hexa 2 as an alternative choice, and we can allocate the space vector to either 5 or 6 according to the logic for finding the subsector. So for any of these overlapping areas, we have 2 alternative realization methods for the space vector. And the first solution depends on toggling the representation between the native representation and the alternative representation, the native vector and the alternative vector choices. Okay. So it is necessary when realizing the vector in a specific sub-hexagon to obtain the small vector coordinates belonging to that hexagon, meaning that V1 and V2, and as a result TA, TB, 20 would be different if we are going to realize a given space vector using the first or the second sub-hexagon vertices of the overlapping areas. Also, it is important to note that the process of alteration should be even, meaning that For every second PWM period, the redundant vectors will be used, while in every first PWM period of a couple of two PWM periods, the other redundant vectors will be used. Okay? Okay. Further check when this method will be effective. Look at this star. This star combines all the overlapping areas, between the subject. Look, if you add all of these overlapping areas together, then you finally reach this star. So for any reference space vector lying within the boundaries of this yellow star, then this method will be effective because for all of these space vectors, we have two redundant representations, either in the native subhexa or the alternative subhexa. Okay, so this method will be effective for a space vector lying within these boundaries. Outside these boundaries, we don't have redundant representation. So this method effect will be limited for space vectors lying in these areas, in the white areas. Okay. So 4 steps are needed to implement this concept. After finding the native subhexa, find the alternative subhexa. Find the alternate small vector alt v1 and alt v2. Find the alternative redundant serial. If the alternative serial not equal to the native serial, then there is no choice, there is no freedom. This is a non-overlapping area. On every first, if they are not equal, then there is alternative. If they are equal, there is no alternative. Okay, so if they are not equal, we have alternative representation. So on every first PWM period, we will apply the native dual time, and on every second PWM period, we will apply the alternative dual time. Else, we apply the native dual time for every PWM period. Else applies to the case where the serial, the alt serial equal to the native serial. Okay, as we say that, we have always a method to find the alternative serial. Okay, and if we couldn't find an alternative serial, then the native serial is the only option. And we need then to consider only the native V1 and V2 and the native T1 and T2. And we have only one representation for the space vector. Okay. Step 1, find the alternative subhexa. How to find the alternative subhexa? Simple logic. For every native subhexa, the one determined by V alpha beta, there are two alternative subhexa should the reference SV is located in an overlapping area. لو كان في overlapping area, if it is in an overlapping area, only one of them is a valid choice based on the logic in the table, which is extracted from the waveform. Okay, look at this. Current subhexa. If current subhexa is 6, okay, look, we say that alternative subhexa is always between adjacent subhexes. Okay, so for example, if we are in the current subhexa 6, okay, and VA is greater than VC, then VA greater than VC. VC, this one. So we are in subhexa 1. Okay, the alternative. Otherwise, it will be 5. Because 1 is surrounded, or 6 is surrounded by 5 to the right and 1 to the left. Okay, so which one of them is the alternative? It depends on the polarity of VA with respect to VC. Okay, the same way in sector 5, we are either alternative is in subhexa 6 or in subhexa 4, based on the check of VA with respect to VB. So it's always a simple choice to find the subhexa if the alternative subhexa if it is existing. Okay, and we know if it is existing from where? From the table of redundancy, this one. As we say, we have 12. These are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 24 combination. 1 and 2 give 2 and 6. 2 and 6 give 1 and 2, and so on. So we have all in all 24 possibilities for equivalent serial. Subtracted from 36, which is the whole space, then we get 12 serials which are having no redundancy. Okay. So coming back, for each subhexa and subsectors, we can find the alternative subhexa and the alternative subsector. As we say that we have 24 cases where a given subsector and subhexa have alternative subhexa and subsector, and this is 24 cases. And the remaining 12 cases, these are the cases where the native subhexa has no alternatives. Okay, and this can be implemented in the form of a table like this, where we give the native subhexa, and using this logic, by converting V alpha beta to V A B C, we get the native hexagon number. From the native hexagon number, also from V A B B B C, we get the alternative subhexa through simple implementation like this. For example, the high voltage and low voltage, VA or VB or VC, according to which subhexa we are in. We compare them, and each subhexa has two adjacent alternative, and this gives us the one which is dictated by the voltage levels. So for V alpha beta small, we get the native subsector number, and we get V1 and V2. For the alternative V alpha beta, recall that we have two parallel paths, the native subhexa and subsector, and the alternative subhexa and also the subsector. Okay, we get the V1 and V2 native and the alternative V1 and V2, the vector values that which we use to get T1 and T2, T8 and T2. It is the same as finding the native small vectors. We give V alpha beta in both cases, that's the two parallel buses which I mentioned, native hexa number and alternative hexa number. V alpha beta, this will give us V alpha beta small, and this will give us alternative V alpha beta small. In all cases, we get also VDC. Okay. After getting this V alpha beta small, sorry, after getting this V alpha beta small and alternative V alpha beta small, we get the offset based on the hexagon number, and we subtract the alpha offset and the beta offset from V alpha beta to get V alpha beta small and alternative V alpha beta small. Okay, fine. Find the alternative redundant serial. As I say, these are the overlapping region. Subhexa 1, subsector 1 is the same as subhexa 2 and subsector 6. Okay, if you translate the entries of this table, you get this 24 correspondences. 2 gives 12, 12 gives 2. 3 gives 11, 11 gives 3, and so on. These are 24 cases. So if you give a native serial from this mapping, there is alternative serial in some cases, in some 24 cases. In the remaining 12 cases, there is no alternative, and we output the same native. Okay? From where we know in which case we are overlapping or non-overlapping, from comparing this resulting with this input. If the resulting is the same as the input, then this is a no overlapping area. But if the resultant is different from the input, then this is an overlapping area, and we can apply the alternative sequence in the every second PWM cycle. Okay. So toggling between native and alternative V1 and V2. This is V1 and V2. This is the original serial. This is the redundant serial. And this is the toggler. Toggler meaning that in a PWM cycle it gives 1, and in the next PWM cycle it gives 0. If it gives 1, then this is the effective serial. And if it gives 0, this is the redundant serial. It is chosen as the effective one. Okay. And this is the alternate signal. Alternate signal meaning that in the case of original signal, the alternate is 1. In the case of alternative redundant serial, the alternate is 0. Okay. And this alternate signal is used to switch between V1 and V1 next or alternative, and V2 and V2 alternatives. So we get what we call V1 effective and V2 effective out of these 4 values. This is effective meaning that this is what we apply to get T1 and T2. Okay, V1 effective, V2 effective, TPWM, VDC, and we get then TA, TB, T0. The values that we use to get the dwell time according to the logic explained earlier. TA, TB to 0, and this is the effective serial. And based on these values, we get T dwell time for the 6 basic switches. Okay. Recap calculation flow. This calculation flow is describing the balancing mechanism using the different degrees of freedom or the redundant vector switching. So we start by reading V alpha and V beta. We find the sub-hexa number and redundant sub-hexa number. We find the small vector, the native small vector and the alternative small vector. We find the subsector number V1 and V2 and alternative V1 and V2. Okay. And then we read the PWM frequency and find the basic serial and the redundant serial, the alternate serial. We arrange equal 1. Does other type of balancing not based on redundant vector swapping do this one? I mean, we say that we have 2 methods. This is the first one of them is using redundant vector swapping. If this signal is equal 1, we go to the redundant, the other method. If it is equal 0, then we check the alternate signal. If the alternate is equal 1, we apply the alternate vector. If it is equal 0, we apply the native vector V1 and V2 to obtain TA, TB, T0. Here, we use the alt serial to find T1A, T2B, T2A, and so on. The 6 duty ratio, 6 duty ratios. Or we find the basic serial to find T1A, T2A, so the whole sub 6 duty ratios. Then we return. So as you see, in some part we have 2 parallel buses, and each of the parallel buses applied for every first PWM period and every second PWM period. We apply this for the alternative for the second PWM period, and this for every first PWM period. Okay. Of course, if there is no alternative, then we have no choice but to apply this calculation flow all the time. Okay. The overall process in terms of SIMULINK blocks, sub-hexa finder based on V alpha beta, we get the hexa number and the alternative hexa number. The same concept applies as we explained before. And by V alpha beta and the hexa number, we get the V alpha beta small, and V alpha beta and the alternative hexa number, we get the alternative V alpha beta small. V alpha beta small and alternative V alpha beta small, we get the alternative V1 and V2 and the native V1 and V2. Okay, was also the subsector number. Using this information, we get the serial. We get also the effective serial and the alternative serial. Using the alternative serial and V1 and V2 and alt V1, alternative V1 and V2, we get the effective V1 and V2. Using this effective V1 and V2, we and the DC voltage and the PWM period, we can calculate TA, TB, and T0. And based on the effective serial, the one which we get from here, we can calculate the dwell time according to the 36 entry or row table. Fine. We finally reached to the testing stage. Here, in the first half of this time duration, we apply the 3-level algorithm without DC, without voltage balancing. As we see here, the upper capacitor and lower capacitor voltage are diverging. One is growing, one is decaying, and ultimately it can reach to full VDC and this can reach to 0. After we apply the balancing mechanism, the two voltage converges, and this is at modulation index 0.3. If the modulation index is turned to be 0.6, then here also this is a divergent voltage, but now it is converging, but the ripple is moving in a wider band. For modulation index 0.8, the band is also increasing. And we see here that the effect of the balancing mechanism is somehow limited, because in this large modulation index, the possibility to have the vector lying in non-overlapping area is high. This is why it is less effective than the small modulation index. Meaning that we need additional method for balancing. So we will go to the second balancing mechanism, which is manipulating alternative zero vector. Exactly as we have explained in 2-level, we have two zero vectors, 0, 0, 0, or 1, 1, 1. Each one of them in the 3-level implementation drives the capacitor voltage in the opposite direction. I mean, if someone is charging the upper capacitor, the other one is discharging the upper capacitor, and the vice versa. And the same effect with lower capacitor. So if we manipulate the distribution of the zero vector, instead of having 2 quarters on the extreme right and left, and 1/2 of the dead time in the middle, we can make this distribution uneven. We can manipulate this division or this distribution in favor of balancing the capacitor voltage. Okay, and there is a simple way to do that. This is what we say. This is the zero vector on the extreme right and extreme left, and is divided by 2, divided by 2. This is T0N and T0B. This division can be, as I said, manipulated. So it's not mandatory to have quarter here and quarter here and half the time here. It can be made even larger here and smaller or narrower here. This is all depending on the unbalanced state. Okay. Using this manipulation mechanism, T1 and T0N and T0B, we have divided the time, as I say, two portions, T0 positive and T0 negative. T0 positive is here, T0 negative by 2 is here. And this division is coming from this calculation. The manipulation factor F is added here to 1 or subtracted from 1, multiplied by the zero vector time and multiplied by half. This this equation or this mechanism produces or redistributes the TO between TON and TOP. And according to this, F should be moving in the range from -1 to +1. Okay, and F should express the imbalance in some way. For example, we get VDC1 minus VDC2. Okay, This is the implementation SIMULINK for this mechanism. And now look, as we have two different values here, it's not simply T0 by 4, T0 by 2, T0 by 4, but we have now T0N by 2 and T0B and T0N by 2. Okay, something is wrong here. This is T0N, T0N. So if we want to calculate the dwell time, for example, this one is not simply Ts minus T0 by 2, but it is Ts minus TON or T0N. And similarly, this one, if you calculate, you will find that it is TB, TB by 2 plus TB by 2 is TB and T0B, T0B. So we need to repopulate the table with the new dwell time based on the uneven division of the of the zero vector time between the T0N and T0B. Okay, so we should have a new table like this where you can find T0N and T0B. And now it is the time to test. Look, here with the old balancing mechanism only in the left half. In the right half, the two mechanisms are applied together, and the result is apparently better. Here is the VDC link difference. It's apparent that it has been improved. And here is VDC1 and VDC2. The same story applies here. There is improvement in the VDC for modulation index that is 0.9. This is 0.5. It's quite normal that for high modulation index, the variation band in the DC neutral point voltage is greater than for low modulation index. It's good to know that midpoint balancing mechanism depend on adaptive reversing of capacitor current polarity. Since no capacitor current flows to load, when the load breaker is disconnected or even a single phase is lost, balancing mechanism may not function satisfactorily during these circumstances. Providing a dummy very light load in this condition may be a good safety practice. This is a used reference. I hope this lecture or this tutorial be useful for you. Thank you.